So thank you very much for coming. We're going to have a new session of our seminar, and this time we have Blum. Jordi helped us inviting him here. We have a very interesting talk on optimization, ants, frogs, and hybrids. So Christian works a lot in meta-heuristics for optimization, which is sort of close to the things we do here. So it's going to be a very interesting talk. So thank you very much for coming. And
thank you very much for inviting me. Well, good morning, everyone. First of all, let's start with the photo here on the first slide. Okay, I thought about showing you some nice view of the city where I'm working. This is San Sebastian in the north of Spain. But when I came here this morning, I saw the impressive view of Santiago. I thought about canceling the photo here. No, but this is a quite small town in comparison to Santiago. So there are 200,000 people living. There are no traffic jams. For sure, you have traffic jams in Santiago. I know it from Barcelona. It's also a big city, and there are traffic jams in the morning, in the afternoon. And I guess in Santiago it's the same. Here, there's nothing like that. It's very well organized. It's really a pleasure working in this city. It's also small enough to be well organized. About the title of my presentation, it sounds maybe a bit strange. Ants, frogs, and hybrids. But this is mainly because instead of talking about a specific topic today, I will give you, let's say, an overview of the topics that I've been working on in the last 3 to 4 years, okay? Also, when we invite people to San Sebastian, I also always prefer that they talk about 3, 4, 5 topics more shortly, okay? Not talking about one topic 1 hour, okay? Just to know what the person is working on, okay? I think it's better to learn what the person is working on actually. So, and the strange title comes from the fact that I have basically 2 research lines, okay? One is swarm intelligence, so I'm working a lot on swarm intelligence issues, always in the context of optimization, but not only on centralized optimization, also on distributed problem solving, okay? And the second line is on hybrid meta-heuristics, so this is the combination of meta-heuristics with any other technique for optimization in general, okay? And I have, for the 2 research lines, I have 2 topics. So first I'm gonna talk about a self-synchronized duty cycling technique that we developed based on or inspired by a mechanism that you can find in ant colonies, where they are awake basically all at the same time and they are asleep basically at the same time. And this is a process of self-organization. And we have used this process for a duty cycling mechanism in sensor networks. The second topic is something quite recent. The first topic is already 3-4 years ago that we were working on this. The second topic is very recent. We used the desynchronization behavior in Japanese tree frogs for graph coloring, but also for finding large independent sets in graphs. Okay. The remaining 2 topics are from the hybrid meta-heuristics field. So the first topic is on an algorithm which is one of the most general algorithms in the hybrid meta-heuristics field. It's called large neighborhood search. Who has heard about large neighborhood search and knows basically what it is? Just for me to get an idea. Okay. So this is one of the most general algorithms in this field, generally applicable algorithms. And then during the last year, we developed an algorithm that we call construct, merge, solve, and adapt, which is, let's say, complementary to large neighborhood search in the sense that we have the impression that it works well for problems where large neighborhood search doesn't work so well. Okay. So these are the topics of today. So let's start with just a very short introduction into swarm intelligence. In a nutshell, we can say it's an artificial intelligence discipline, okay, where the goal is designing intelligent multi-agent systems and taking inspiration from the collective behavior, that is important, of social animals like ant colonies, flocks of birds, and fish schools. Okay, so here on the left-hand side, you have a termite nest. You see the person here standing beside. So this nest is about 5 meters high, has a very complex internal structure. And the amazing thing is that the termites don't know how to build that, even though they are building that in cooperation. Okay, so they have a different way of solving problems and realizing tasks. Okay, which is based on a set of simple rules of how to react to the environment being in a certain state. Okay. And following these simple rules, they can build complex structures. Another example of swarm intelligence is the migration of birds. When they migrate, they fly in this V shape. I'm sure all of you have seen that. And this has evolved, let's say, during evolution. All of these mechanisms have stayed in evolution because of a good reason. And the good reason in this case was energy saving. Okay, they simply save quite a lot of energy when they fly like that. As a swarm, okay, as a group. On the right-hand side, we have a fish school. So this has also, I mean, they move all seemingly at the same time, staying close together. And the reason for this having evolved is basically protection against predators. Okay, when predators see the fish school, they get confused and don't know which fish actually to pick. Okay, so the properties of these swarm intelligence systems are as follows. They consist of simple entities, ants, termites. They don't have a brain power. They don't have power for reasoning. So that's why they have developed actually other ways of problem solving. Okay, they are distributed. This means there's no global control. Actually, until the 50s of the last century, biologists still thought that, for example, in beehives, the colony, the queen would know actually how to do things and would give orders, okay, to the other bees, but this is actually not true. Actually, these systems, they work by self-organization, and self-organization is a result of different ways of communicating between the ants or the bees, okay? There's a first way of communication, which is the direct communication, which could be visual or by chemical contact. And then you have the indirect communication, which is often the important aspect for swarm intelligence. And this indirect communication has been labeled stigmergy by a French biologist called Grasset in 1959. And stigmergy works basically in the following way. So E means the environment, okay, and the index, the sub-index means the environment being in different states, okay. So E1 means the environment is in a certain initial state, triggering a response of the colony. R means response. The response of the colony changes the environment in some way. This again triggers a different response, and so on, until at the end the environment is in a state where the problem solving has stopped. Okay. So, for example, if we apply this to nest building, then here the nest would have been built. Okay. So the result is that they solve complex tasks in cooperation. And these are other examples of swarm intelligent behaviors. So the cemetery formation, for example, that you find in ant colonies, they tend to pile up the corpses of dead ants in certain places. Okay, this has been used for clustering, for example. Then you have the self-synchronized flashing of fireflies. This has been used also in applications in sensor networks, for example, synchronization applications. Optimal food source exploitation in honeybees. This has been the inspiration for the bee colony optimization algorithms that we have in meta-heuristics. Shortest pathfinding in ant colonies, of course. This has been the inspiration for the ant colony optimization meta-heuristic. And the self-organized nest building. I know that 10, 15 years ago, there were people actually trying to take profit from these nest building behaviors for automized construction. For example, NASA was at some point maybe they still do that, thinking about automized construction on Mars. Okay. So that everything would be built before people actually can be shipped there. But I don't think it has led to anything substantial yet. Okay, but let's start with the first topic then in swarm intelligence, the self-synchronized duty cycling in sensor networks. So in ants, we find synchronized activity patterns, which means that at some moments in time, nearly all of them are awake and working on specific tasks, and at other moments in time, they are sleeping or resting. Okay, and this has been evolved because of information propagation. So when all of the members of the colony are basically awake at the same time, information propagation is much more efficient. Okay, or information sampling on the other side. And this has been modeled in this paper here, okay, from 2000, and they modeled it by means of automata. Okay, so this is the model. This model is very simple. Each ant is modeled as an automaton, and it has a continuous state variable Si, and T just means the value at time T. Okay, SIT is the value of automaton I at time T. These automata, they move on an L time L grid, which with periodic boundary conditions. And at each time step T, an automaton is either active or inactive. And this depends on the value of the state variable, okay? And on the activation threshold. So here in this formula, we have the state variable, we have the activation threshold. And if this value is greater or equal to this one, to the activation threshold, then this function will evaluate to 1, and the automaton is active, okay? If this value is smaller than the activation threshold, it will evaluate to 0, the function, and this means the automaton is inactive, okay? Now, we can simulate the following simple algorithm, okay? So all automata are at some place in the L time L grid, and in each iteration, we calculate the activity of the automata. Each one is either active or inactive. If it is inactive, then it might spontaneously activate with some probability, and the activity level is set to some parameter. And after this, they move. All the active automata move to a free position in the 8 neighborhood of the grid, okay, if possible. The last step is the state variable update. Okay, the new value of the state variable depends on the old value plus the sum of the state variable values of the neighbors in the 8 grid, in the 8 neighborhood in the grid. Okay, and then we take the hyperbolic tangents of this value, and this is the new value of the state variable. Now we can, at each iteration of this simple algorithm, we can measure the proportion of active automata, okay? And if we do that, we get something like that, okay? 0 means all of them are inactive, and 1 means all of them are active. And what we get when we simulate this algorithm is an oscillating behavior. So at some moments in time, nearly all of them are awake, and at other moments in time, nearly all of them are resting, okay? So now we use that for building a duty cycling protocol. Duty cycling in sensor networks is sometimes necessary for saving energy, okay? Because sensor nodes, they might only have a task every 2 hours or something like that, or periodically, okay? So being awake between measurements, for example, is simply unnecessary and wastes energy, okay? So the protocol that we developed has the following structure, that in each communication round, so from 0 to delta is 1 communication round, and this communication round has a first phase, very short phase, where all of them are active, and there they interchange information, and then where they also decide if they are awake or asleep in the user application time of the communication round. Okay, so this is the general outline of the protocol. Exactly, and each node in this first phase here of each communication round randomly chooses a time for executing its duty cycling event. I will tell you now what this is. Okay. In this case, we deal with a static sensor network, so they don't move. Okay, but later we have also applied this to mobile sensor networks, and it works in the same way. Now, in addition to state variable value and what I told you from the model, each sensor node has also a battery, okay, and the battery level between 0 and 1. and it maintains a special message queue, QI, for the communication concerning the duty cycling, okay? It's also equipped with a radio antenna that can choose between different transmission power levels. Okay, for example, the sunspot technology offers to choose different transmission power levels in the radio antenna. The contents of such a message, a duty cycling message, is the sender node's state variable value, simply. Okay. Now we also added a energy harvesting facility, for example, a solar panel or something like that. Okay, and this is the sun intensity, let's say, that schedule that we used in our simulations. But this is exchangeable. It could be any. Okay. Now, this is the duty cycling event. Okay, so you remember that in the first phase, in this short phase of each communication round, where all of them are awake, each one chooses a random time where it executes this event. Okay, so first of all, it calculates if it's active or inactive in the user application period, which is following this phase. Okay, it might spontaneously activate. Okay, this is this part here, and then depending on the battery level, we choose a transmission power level. So if we have a few battery left, we choose a lower transmission power level. When we have a full battery, we send as far as possible. Okay. We compute a new value of the state variable, and then we send the new value of the state variable to all the neighbors. Okay, with the transmission power level that we have chosen before. Now, when we simulate that, we get something like that. Here we have the time steps, okay? Here we have the proportion of active sensor nodes. The red line here is the average battery level of the network. The green line is the sun intensity, and the blue line is the proportion of active nodes at any moment in time. Okay, so we see that first of all, there's an oscillating behavior, like in the automata model. But second, it also adapts to the battery level now. Okay, so when the battery level drops, the activity peaks are not as high, and the periods when the sensor network is basically sleeping are more frequent. And when the battery level rises due to energy harvesting, we see that, for example, in this period, there's even no necessity that the sensor nodes switch off, go to sleep. Okay, so this is an adaptive mechanism now that we developed on the basis of this automata model. Now, in the slide before, we didn't consider packet loss. If you consider packet loss, then here we have the packet loss rate. Okay, so it's 0, we don't have packet loss, and we have more and more packet loss if we go to the right. And on the y-axis, we see the mean activity of the system. This was 0.6 on the slide before, on average. We see that until a packet loss rate of 30%, we don't lose functionality of the system. Okay, this means it's very robust. Okay, only after 30%, the functionality goes down, let's say. Okay, so this was the first topic. Just to give you an idea, not in a very deep way, but maybe if there are some questions, we can do that now, because otherwise maybe you forget about them. Or so if there are some questions, yeah.
Just, I mean, I get from what intercommunication is for packet loss. In this case, what would packet loss mean?
That a duty cycling message, which actually should reach one of the neighbors, doesn't reach it for some reason. Okay.
So the next question is the swarm update.
This comes from the model. Yeah, this comes directly from the model. I mean, this formula for updating the state variable values comes directly from the model, and it worked best. Let's say they try different functions, And this is the function that gave them the behavior that is more close to what they saw in nature than any other function they tried. Okay. So if there are no more questions, we can go to the next slide. These frogs are actually created by one of my colleagues in San Sebastian. So he was painting them. He did a whole poster about this work we did for one of the conferences. I mean, he's very talented, obviously. Okay, he did a whole poster, and I just show you one of the images here. So the question was if frogs can color graphs, and it turned out that they can. So now the application is graph coloring and also finding large independent sets in graphs. So just, I'm sure most of you know what graph coloring is, but we have a graph, okay? And the goal is to assign a color to all the nodes such that neighboring nodes don't have the same color and such that the number of colors used is minimal, okay? So for example, in this graph here, an optimal solution would be this one here. So no neighbors have the same color, and the number of colors used is 4, and we don't find a valid coloring with 3 colors. Okay, it's impossible. This problem is in a centralized setting is NP hard, but we wanted to try to solve that in a distributed way. Okay. That you cannot find an algorithm that runs in polynomial time and gives you the optimal solution. Yeah, in a distributed way, it's NP hard, okay? But when you say NP hard, you talk usually about centralized algorithms. You refer to centralized algorithms, not to distributed algorithms. Okay. But it's an NP hard problem. You don't find any algorithm, neither centralized nor distributed, that is polynomial and solves the problem to optimality. Okay. This is the other problem that we tackled. It's very related to graph coloring. It's about finding large independent sets. An independent set in a graph is a subset of the nodes such that no 2 nodes of the subset are connected by an edge. Okay, so a trivial case is this one here. The black nodes are always the members of the independent set. Of course, if you only have 1 node, it's an independent set. This here is a maximal independent set because we cannot add any of the white nodes without destroying the property of being an independent set. And this one here is a maximum independent set because among all maximal independent sets is the largest one we can find. Okay, solving this problem here, finding a maximal independent set is actually in P. Okay, it's not NP hard. We find polynomial algorithms to do that. Finding the maximum independent set is NP hard. Now, there's of course a strong relation between graph coloring and independent sets. Given a graph coloring solution, each color class, which means all the nodes having the same color, are independent sets. But it doesn't mean necessarily when you have the optimal coloring solution that this contains an optimal independent set solution. This is not the case. For example, here the optimal coloring solution has 4 colors. All the color classes have 2 nodes. So the largest independent sets in this solution are of size 2. And this is the optimal. This is the maximum independent set you can find in this graph. Okay, so there is some relation, but it doesn't mean that when you have an optimal solution to this problem that you have an optimal solution to the other one. Now, let's first of all talk about the biological inspiration of that. Okay, the biological inspiration is the desynchronization behavior in male Japanese tree frogs. So what they do is they are calling, and their calls attract the females. So the females, they listen to the calls, choose one of the males, and move into this direction where they hear the calling. Okay. What happens is when 2 frogs that are heard by the female call at the same time, the female cannot distinguish between them and cannot find the direction. Okay. So this is why in evolution they desynchronize their calling. Okay. Just to get the the women coming to them. Okay. Yeah, that was that slide. Now there were biologists that modeled this behavior, this desynchronization, and this is done by a model that is based on pulse-coupled oscillators. I won't explain you the model, I just explain you what it does, basically, okay? So you have oscillators. Some of them are coupled, some of them not. The ones that are coupled means that they represent frogs that are in hearing distance to each other in respect to the female, okay? Other frogs, they might be too far from each other, so the female can either hear this one or this one, then they are modeled by oscillators that are not coupled, okay? Now this is basically what the model does. Each oscillator has a phase value between 0 and 1, which can be represented here by a circle. So this point here corresponds to values 0 and 1, and the circle corresponds to all the values between 0 and 1. Okay, so we place the oscillators on the place on the circle where their value is, basically. Okay, so in this example here we have two oscillators that are coupled. You don't see in this example that they are coupled. I just tell you they are coupled, and they start with values that are very close to each other. Okay, this would be a bad situation for the female. Okay, so the model now tries to push the values, the phase values of these oscillators apart from each other as far as possible. And this would be on opposite positions on the circle. Okay, so the difference in value would be 0.5. This is the maximum difference you can get. And this is, when you have two coupled oscillators, the model works perfectly. Okay, so no matter what starting values you have, this will always be the final, the attractor of the model. Okay, this is where it converges in a situation where the two are opposite each other on the circle. When we have other topologies, for example, here we have a topology where we have 4 oscillators, and the edges means that 2 and 3, for example, are coupled, 3 and 4 are coupled, and so on. Okay. Now, in this case already we have other attractors, not only the optimal solution. The optimal solution is this one, okay, that 1 and 3, because they are not coupled, have the same value at the end, and 2 and 4 that are not coupled have the same value. This would be the optimal solution. But you have also this solution where the system sometimes converges to, that the values are distributed with 0.25 distance, okay? So it's not a perfect model. In this case here, this would be the optimal solution, okay? You couple again, you join, you give the same value to 1 and 3 and the same value to 2 and 4, and 5 has a value as far apart from the two others as possible. Okay. But anyway, we used this model and implemented a graph coloring algorithm again in the context of wireless networks. Okay. The algorithm works with communication rounds of 1 time unit length, and each sensor node now in this case has this phase value, okay, like in the model. And the phase value is actually used to execute a short program at time delta I. Okay, so the phase value determines the time in each communication round when the sensor node executes its short program. And the second value each sensor node has is the current color. Okay, a color. Now this is the program that each node executes at time delta I in each communication round. So first we recalculate theta. I will show you on the next slide how this is done. This comes actually directly again from the model. And then it chooses a new color Ci. Then it sends a graph coloring message M to its neighbors and clears its message queue. Okay, and in this graph coloring message, we have actually this theta value of the sender and the current color of the sender. So when a node sends this graph coloring message, it puts in the message its color and its phase value. Okay. This is the way in which the theta values, these phase values are recalculated. So the new phase value is the old one minus some term which depends on the face values of the messages received from the neighbors. Okay? And for pushing these values apart, we use the sinus function in this case. Again, this was the best function, the function that worked best for this model. Okay, and choosing a new color is also very simple. At the time a node chooses a new color, it chooses the color to be the minimum color that is not already chosen by one of its neighbors. Okay? Now, this is a distributed algorithm, so the algorithm itself doesn't know about the quality of the solutions, doesn't know that it creates solutions, but we can check the solutions during the course of the algorithm. Okay? And this is a typical run of the algorithm. So here we have the communication rounds on the x-axis. On the y-axis, we have the number of colors used in the current coloring, because in each communication round, we have a valid coloring, okay, a valid solution. And you see that this number of colors is generally going down, which is a very good sign. So the algorithm is improving over time, okay? Now we applied this algorithm to different sets of graphs, for example, to Dmax graphs, random graphs, grids, and so on. And we compared to at that time the best algorithm for distributed graph coloring, which was from this paper. And here on the y-axis, you see the improvement for sets of graphs of our algorithm over the one from this paper. Okay, you see two bars here, the white one and the gray one for each set, because the white one is the improvement of the algorithm I just showed you, and the gray one is an extension of this algorithm where we use additionally a distributed local search for improving the solutions. Okay, this distributed local search, you see that it's improving always slightly the algorithm. Just in one case, there's a substantial improvement in the case of grids. Okay, in the case of grids, really, we have a substantial improvement by the addition of this distributed local search. Okay, we also used this algorithm because looking at the behavior of this algorithm, we had the impression that the graph coloring solutions that it generated were also good independent set solutions, contained in good independent set solutions, even though knowing that having an optimal graph coloring solution, we don't have necessarily a good independent set solution, okay? So we applied this algorithm also to independent set because we had this impression that it generated colorings of that contained good independent sets, and compared it to an algorithm which was published in 2011 in Science, which is a very interesting algorithm which is based on the development of the nervous system of the fruit fly. This is why we call it fruit fly. In the original paper, they don't call it fruit fly, but well, as we worked with frogs, we thought it might be a good idea to call it also according to the animal that inspired the algorithm. And the results are basically as follows. So here we have a table which is on geometric, random geometric graphs, okay? And going down this table, we have sparse graphs on the top. Each line is for 10 random graphs. Sparse lines on the top, and the graphs are every time more dense, okay? So we go from sparse to dense graphs. These graphs are on 100 nodes, so they are rather small. And you see on the blue background here that our algorithm always outperforms the other one, okay? Now, when we go to larger graphs, what happened was that at some point, here at some density, fruit fly was getting better solutions, but on the cost of a much higher number of communication rounds. Okay, so that, well, this is always the trade-off you have in all the optimization algorithms, no? In this case, it was very obvious. Our algorithm always used around 700 communication rounds, and here, when the algorithm, the fruit fly algorithm, started to be better, it was really going up the number of communication rounds needed. Okay, so this is basically the comparison between the two algorithms. Then we also studied, let's say, the number of nodes that used specific colors. Okay, so on the the two bars here on the left, they show the number of nodes used in the most used color of a solution. Okay? The second, the third and fourth bar here, they show the number of nodes used in the second most used color of a solution. Okay? And now the light blue and purple colors, they show the solutions from the first round of the algorithm, light blue, and purple, the solution when the algorithm converged. Okay, and we see clearly that at the end, when the algorithm converged, the most used color is used much more often than in the first round solution. This means actually that the algorithm converges to solutions which contain good independent set solutions. Okay. Okay, so this was the part on the frogs. So if you have any questions, maybe now is the time to ask.
Sorry, can you mention how does the fruit fly algorithm works?
No, but it's also a distributed algorithm. Okay, so it's also based on local communication between the nodes. And it uses a specific mechanism which is used in the development of the nervous system of the fruit fly. But I didn't explain it how it works.
But it's not easy to explain.
No, it's not so. It's not so easy. Okay. So if there are no more questions, we move to the second part. And I see I've already used up quite some time. If this clock goes well. Yeah. That's correct? Okay. So let's talk about two topics on hybrid meta-heuristics now. Okay. So first of all, what is a hybrid meta-heuristic? The problem is for some people, sometimes I got the criticism that there is no precise definition of a hybrid meta-heuristic. Now, where's the line, let's say, when you call an algorithm a hybrid algorithm, and when don't you call it a hybrid algorithm? It's very difficult to say sometimes. Okay, some people call a hybrid meta-heuristic already the combination between evolutionary algorithm and local search. Okay, mimetic algorithms, for example. Some people call them hybrid meta-heuristics. I don't know where the line is, but it doesn't matter really, because we can simply give a characterization. We can say it's an algorithm that is based on a combination between a meta-heuristic and any other technique for optimization. Okay, and this any other technique might be a meta-heuristic, might be branch and bound, dynamic programming, or simply general purpose ILP solvers like Cplex or Gorobi or something like that. Okay. So why are people talking about hybrid meta-heuristics nowadays? Because at the beginning, the communities in optimization, I think they were quite isolated. They didn't look much over the border and didn't look much what the others were doing. Even within the meta-heuristics field, people from Tabu search at the beginning didn't look much what the evolutionary computation people were doing and the other way around. Or even if you go even further down within evolutionary computation, you had different strands at the beginning where people didn't look really what the others were doing. No? And at some point, this changed. And I would say about 10, 15 years ago, the body of research on hybrid meta-heuristics was growing. And this is shown by the starting dates here of some of the conferences in this field. IIIO, for example, was held for the first time in '99. Some colleagues and I, we initiated the workshop series on hybrid meta-heuristics in 2004. And math heuristics, which is more specific, which only looks at combinations of meta-heuristics with mathematical programming techniques, was started in 2006. Well, nowadays I would say it can be called a new, its own line of research. Okay, and one of the most generally applicable algorithms in this field is large neighborhood search, which is a quite simple algorithm based on a simple principle. So the principle is use of an efficient, exact technique for finding the best neighbor in usually a large neighborhood of a current solution. Okay, you have a current solution, you define a large neighborhood. This means a neighborhood where you have many solutions inside, and then you use an efficient, complete technique for finding the best neighbor. Okay, and this is the general trade-off that you have in local search. So when you want to do neighborhood search, okay? So when you have a small neighborhood, the advantage is that it's fast to find an improving neighbor, okay? So for example, a 2-op neighborhood in the case of the TSP, it's fast to find an improving neighbor. The disadvantage is that the average quality of the local minima can be very low. On the other side, when you have a large neighborhood, then the advantage is that the average quality of these local minima is much higher, but the disadvantage is that finding an improving neighbor might be a very difficult problem itself, okay? Even NP-hard sometimes. And then you have different ways of examining these large neighborhoods. And you might do that heuristically, or you might do that with some efficient exact technique, which is sometimes possible. Now, we applied that, I just want to give you one short example. We applied that about 4 years ago to a problem from bioinformatics, which is called the founder sequence reconstruction problem, okay? And I won't give you the background of this problem. I just tell you the technical description of this problem. So in this problem, we have given such a binary matrix here, and it's called a recombinant matrix. And each line is a recombinant, okay? So with 5 recombinants here. Then we are looking for a number of founders, and this is actually a solution to the problem, okay? So the number of founders is given. For example, you have to find 3 founders, like in this case. And the founders, they have the same length as the recombinants, and they are also binary strings. And now, given a founder, calculating the objective function value is done in this way. So with these founders, you try to represent the recombinant matrix with the least number of breakpoints. Now I explain you what breakpoints are. So for example, if you want to regenerate, let's say, this first recombinant with these founders, then you can take 1, 1, 0, 1, 1 from B, because this has 1, 1, 0, 1, 1 in the same positions. But then we have 0, 1 here, which we don't have in B, but we can take it from C, okay? And this is what you see here. So for the first recombinant, we take the first 5 positions from founder B, and the last 2 positions from founder C, okay? And this is a breakpoint. We have to change founder in order to represent this recombinant, okay? We can do that for the whole recombinant matrix, then we get something like that. And for this solution here, we have 4 breakpoints. This is the objective function value, and this value must be minimized. So we want to find the founders such that the number of breakpoints are minimized. Okay, this is the problem. It's also NP-hard. And there is a very efficient branch and bound technique, which is called RecBlock from the literature. So this is the paper where this was published, which works basically up to 3, 4 founders. Okay, so if I only want to find 3 or 4 founders, then I can use RecBlock, and this is very efficient, gives me the optimal solution. The problem is, what can we do when we want to find more founders? Okay, then we can apply a large neighborhood search, for example. And we can do it in the following way. So first we generate an initial solution with some heuristic, for example. So we generate a founder matrix, an initial founder matrix. So let's say in this example we have to find 7 founders. Okay. Then we fix some of these founders, so we leave them as they are, and we destroy randomly chosen, let's say 3 of the founders, like number 3, 5, and 6. They are destroyed. And now we use RecBlock in order to find the best 3 founders here, given that 1, 2, 4, and 7 are already there. Okay, this is as efficient as only finding 3 founders. Okay, we can find in this sense the optimal neighbor in this neighborhood, because this is a large neighborhood. This is a very large neighborhood. We are looking for all the solutions that we can get. The neighborhood consists of all the solutions that we can get by putting in here the all possible binary strings. Okay, it's a very large neighborhood. But RecBlock gives us the best neighbor in a very efficient way. And this is what we do iteratively. Okay, we have the current solution: destroy randomly 3 founders, use the RecBlock algorithm to give me the best neighbor, and this is the new current solution. okay? And then the algorithm goes on. And actually, I don't show you results in this case, but until nowadays, I think this algorithm is the best one you can find for this problem when you are looking for more than 3 or 4 founders. Okay. Any question about large neighborhood search? But the principle, I think, was getting clear. No? Okay. Now, our impression was that, of course, we don't have a theoretical proof for that, but the impression looking at papers and implementing large neighborhood search yourself was that large neighborhood search basically works well when you have a number of variables in your, let's talk about integer linear programming, okay? When you have a number of variables in your ILP that is linear in the input parameters of the problem, okay? So when you don't have too many variables, you can have an exponential number of constraints, but when you don't have too many variables, large neighborhood search usually works well. On the other side, the impression was that when you have an exponential number of variables, that large neighborhood search was getting lost, was not giving you good solutions. So we thought about what algorithm can we use? How can we use, talking about ILPs, how can we use a general ILP solver, like Cplex or Gorobi, even in the context of large problems, when the problem has a large number of variables, okay? And this is our first approach, let's say, which was published for a specific problem this year in Journal of Heuristics, and we are in the process of writing a journal paper on that. So this is a different way of expressing this observation. So in the presence of a large number of solution components, I call them solution components from the meta-heuristics point of view. Solution components are basically variables in the ILP, okay? So in the presence of a large number of components, many of them can only lead to bad solutions, okay? So the idea is exclude presumably bad solution components or bad variables, useless variables from the ILP, okay? So the steps of this method are as follows. We iteratively generate presumably good solutions, rather good solutions in a probabilistic way. For example, if we have a greedy heuristic for our problem, we can use it in a probabilistic way in order to generate different solutions. Then we assemble a sub-instance from the used solution components, or talking in the context of variables, having our set of solutions, we know for each variable which values did it take in these solutions, okay? And we use these subdomains of the variables in order to generate a sub-instance. And then we solve this sub-instance by means of the ILP solver. And this sub-instance is usually much smaller than the original problem instance. So the ILP solver should be efficient for these sub-instances. And then we delete useless solution components from the sub-instance at some point, because it might be that our constructive algorithm generates solutions with components that will never appear in near optimal or optimal solutions. Okay, so keeping them in the sub-instance is inefficient at some point. So we should try to get rid of them. Okay. So this is the algorithm that we developed based on this idea. So let's go slowly through this slide. So C is the complete set of solution components, okay, given our problem instance. This might be in the TSP case, this is the set of all the edges of the graph. C prime is always the subset of the solution components that indicates my subinstance. C prime is my subinstance, okay? And then we give to all solution components, we give them an age which starts at value 0. At the beginning of the algorithm, all the components have age 0. Now we iterate these 4 steps in the algorithm. First, we probabilistically generate a number of NA solutions, and this gives me a set C hat of all the solution components used in these NA solutions. Then all these components that are in C hat and not already in my sub-instance, I add them to the sub-instance. And I apply an ILP solver to solve C prime, the sub-instance C prime, to optimality. Okay, this gives me the optimal solution for the sub-instance. Then the next step is to increment the age of all the solutions in my sub-instance and to set the age of all the components that are in the optimal solution of the sub-instance to 0. It's like a reward, okay? And the last step of each iteration consists in removing all components from the sub-instance that have reached the maximum age, okay? Reaching the maximum age means that in the last X iterations, this component has not appeared in the optimal solution of the sub-instance. So this is an indication that we can get rid of this component, okay? We have applied this algorithm to several problems, okay? One of them is the minimum covering arborescence problem, okay? In this problem, we have given a directed graph, which is rooted in a certain node, and has weights, positive or negative weights on the links. And there's also a subset of the nodes which are painted in black here, which must be in all the solutions. Okay, solutions are arborescences, and any arborescence in such a graph is a solution. An arborescence is a directed acyclic graph rooted in the root node, okay, a subgraph basically, which contains all the black nodes, and the optimal solution is the one that has the sum of the weights here of the links that are in the solution minimal. Okay, so you want to minimize the weight of an arborescence. This is the problem. Now, in order to apply our algorithm, we just need two components: an ILP model. Let's say, if we talk about ILP solvers, an ILP model, and a way of generating probabilistically solutions. Okay, the way of generating solutions in this case is very simple. We start from the root node and add at each step one of the links that go from one of the nodes already in the solution to one of the nodes that are not in the solution. Okay, and the probability for choosing these links is proportional to the weight of these links. So the lower the weight of a link, the higher the probability to be included. Okay. Now, in principle, we could stop such a solution construction once all black nodes are included in the solution. But it has shown that when we construct spanning arborescences, okay, so we stop once all nodes are included in the solution, gives us better results of the algorithm. Okay, so that's what we do. We generate spanning arborescences in a probabilistic way. And then we use this ILP model for solving the sub-instances. Okay, this ILP model has for each link, it has a binary variable. Is it included in the solution or not? Then the first set of constraints says here that for each node for all incoming nodes or incoming links of a specific node, at most one can be chosen. This set of constraints says for all black nodes, one link must be chosen, one incoming link, because they must be included in the solution. And this set of constraints says that when I have included the link, then there must be at least one of the links included that point to the tail of this link. Okay, in order to have a connected. These are the connectivity constraints. Okay. So don't look at the numbers. I will just explain you the general impression of the results. Okay, so here we have nodes of different graphs of different size, 500 nodes, 1,000, 5,000 nodes. Yeah. Yeah, the model solves the problem, but
the problem is that the model is too big for sequence.
Yeah, yeah. So you will see that. Yeah. So we use the same model. We use it for applying it to the original problem, but also within our algorithm for solving sub-instances. Okay. So we have graphs of different sizes here, and of different densities. So these are the edge probability values here used to generate these random graphs. And we compare three algorithms. So the probabilistic greedy algorithm that we actually used for generating the solutions within our algorithm, Cplex applied to the original problem instance, and our hybrid algorithm. Okay. Now the results with the blue background here are always the best for each line. Okay, we can see that, and here you see the gap values also for the solutions produced by Cplex. This means that for nodes, for graphs of 500 and 1,000 nodes, Cplex solves the problem. Okay, we have gaps of 0. Cplex always gives us the optimal solution within a certain computation time limit. Okay. Comparing these results to the ones of our hybrid algorithm, we can see that in most cases, our algorithm also generates the optimal solution, not knowing that it's the optimal solution, but it reaches the optimal solution. There are just some cases here. Each line is again for 10 random graphs, okay? So there are 1 or 2 graphs here where we don't find the optimal solution, and one or two graphs here where we don't find the optimal solution, okay? The time is also very low. Okay, even so when we go to the biggest one of these graphs where Cplex is able to solve the problem to optimality, we can see that we are doing that faster. Okay. And then when we go to 5,000 nodes, Cplex is not able to give us even feasible solutions. Okay, and there where our algorithm is really useful. Okay, here we get in comparison, we can only compare to the probabilistic greedy algorithm, but it significantly outperforms the probabilistic greedy algorithm. Okay. Also, I could add that solving these sub-instances, the sub-instances are usually of size 2, 3, 4, 5% of the original problem instance. So Cplex was always very, very efficient in solving these sub-instances. It took usually a fraction of a second. Okay. And this is why we think that this algorithm is so efficient. Yeah.
In the Cplex column there,
yeah.
The problem there is memory, or is it?
The problem in this case is memory. Yeah. The problem is memory in this case. But we have another case where the problem is simply computation time.
Because you see there's a time limit there.
Yeah, but it's not meaningful in this case because the model doesn't even fit into the memory. Yeah, the model doesn't fit into the memory. Okay, but we have another case where the model fits into the memory. At some point, Cplex gives you some solution, but a very low quality solution within a certain computation time limit. Okay. Okay, so other applications, we have another arborescence problem to which we applied this algorithm. Also a problem from the bioinformatics field, minimum common string partition. And now we are also working on 2 other problems where we already see that the results are very good. Okay, so possible research directions in this algorithm, there are many. And some of them are, for example, to have adaptive probabilities during the solution construction over time. Because at the moment, we are using the same probability distribution for generating solutions. But it might be possible to learn this probability distribution over time in order to change to other areas of the search space. Okay? A more intelligent version of the aging mechanism, because our mechanism is black and white. Either you are in or out. Either you have reached the age limit and then you are out, or you are still in. Okay, but there might be something in between. There might also, what we talked yesterday, be a relation in some problems to column generation, because it's very related to column generation in some sense. And we might be able, for some problems, to use the pricing information from column generation or to generate new solutions. Okay. So this is all future research, and well, this will take years. Okay, so thanks for your attention, and if you have questions about the last part, please ask.